Hi, everyone. Give me 1 second. Let me get the problems. Okay, can you all see the whiteboard now?
Yes.
Okay, good. 361 is correct. Let's see. Neil, can you explain?
So yeah, there it says that there's a square shaped floor, which is with congruent square tiles. That means that the square tiles are all the same length. And if the total number of tiles that lie on the two diagrams is 37, how many tiles cover the floor? So the diagonal, it's from like the top left to the bottom right. That's like one diagonal. And so this is basically one diagonal. And then the other diagonal is from there to there. So I knew that with the two diagonals, then there is one square. So there's a bunch of squares everywhere, and we don't know the amount. So all we know is that it's going through, and that on the two diagonals, there are 37 blocks that are between the two diagonals that are in, so 37 blocks in all that are in both diagonals. And so that's the total amount. So basically there's in the middle, there's one block, which basically both of them are intersecting. And that means that block is for both this diagonal and this diagonal. So that leaves us with this being 19 and this being 19. And basically there are that, and since all of the numbers are all of the squares are congruent and they're all the same size, then this is 19. All of the sides are also 19. This side, and this side. So basically we're supposed to find the number of tiles that are inside. So all of this part we're supposed to find out. And the formula is for finding the area of a square is side squared. So one side is 19, so you do 19 squared and get 361.
Good. Yep, that's correct. Yeah, so I think the key kind of thing here is to first, once we know the diagonal if it's square floor with congruent square tiles, we see that when I draw one of these diagonals, as Neil showed us, it basically intersects one square in each row here. And we're going through the diagonal of each of these squares as well. So if this whole thing was like an n by n square, or let's say 10 by 10, this diagonal would go through 10 squares. And we can see this if we draw 4 by 4 or 3 by 3, the diagonal would go through 3 squares. So we don't know what it is here. So let's just say it's n or some number of squares. We know it'll go through that many tiles. Now, if I do the same thing with the other diagonal, it's the same result. I'll again go through n squares on this diagonal. The only kind of overlap is this one square in the middle. There we see that both of these diagonals intersect and they go through the same square. Otherwise, you can think about each of these squares will be different from each of these. So if these two go through n squares each, but this one is getting counted twice. So we know that total the squares that are passed through by both of the diagonals would be 2 times n minus 1, which would be equal to 37. We know there's 37 tiles that lie on the two diagonals. This gives us n is equal to 19. So this means that the square is a 19 by 19 grid of tiles. So the number of tiles that cover the whole floor must be 19 times 19, which is 361. Any questions on this? Okay, let's move on to the second one. Okay, good. 20 is correct. Sanvi or Dhanush, can one of you explain?
So what I did was people are seated at this table in such a way that the next person seated must sit next to someone. So what I did was if I put two people together and then leave a gap and then put two more people and then leave another gap, people are technically still sitting next to each other. So I went up to 4 people with the gap and then I stopped there and I got 20. But I didn't do the rest of the problem because I'm not sure if you could actually go on to do an 8 people gap. So I only went up to 4 people gaps.
Okay, good. Let's look at kind of what that would be. So if I put the first person here, where would I put the next person in your kind of setup? So you said in 4 people increments, right? So the next one would be here, right?
Yeah. Sorry.
Okay, good. Yeah, so let's look at this. So let's first confirm that 20 works, and then we'll think about why we can't get lower than 20. So if we look at this, we'll imagine putting essentially one person here and then 2 blank spots. One person here, 2 blank spots. A person here, 2 blank spots. And we know there's a total of 60 chairs, right? So essentially there would then be 20 people, and after each person, there would be 2 kind of empty seats in the table setup. Now let's think about this. If I keep going, and so we know 1 person, 2 empty seats, and so on, and there'll be 20 of these kind of triples in the whole circle. Is it possible now to put another person without sitting next to one of the people who are already there? So if I put someone in any of these 2 spots, right? If I put someone in this spot, they would be next to this person. If I put someone in this spot, they would be next to this person. So we know by putting a gap of 2 people between 2 people who are seated, if someone sits at either of these, they would be sitting next to one of these people. So a gap of 2 essentially ensures that if someone sits at either of these spots, they would have to be next to one of the existing people. Now, what about if there was a gap of 3 people?
3 people works because there's an empty chair on either side of the person.
Good, yes. So in this case, I could just put one new person here, and they would not be seated next to someone who was already there. They essentially would be seated, they would be next to 2 empty chairs here. So if I did put 3 empty chairs between 2 people, this property won't be satisfied. So we know that people are seated in a table such a way that the next person seated must sit next to someone. If I put 3 people, 3 gaps between 2 people, one person could sit here and violate this property. So this means that I know the maximum kind of gap between any 2 people at the table must be no more than 2 seats. So this means that whenever I put one person seated, I can have at most 2 gaps next to them before I have to put the next person. If not, if I put more than 2 gaps, then this property won't be satisfied. So this kind of helps us see that this is the best we can do. So we put one person, we put 2 empty seats next to them. We put a person, 2 empty seats next to them, and so on. So if we have a total of 60 chairs, we can essentially group it into groups of 3. So 1 person and 2 empty seats and so on. So we can do up to 20 people. Each of the 20 people would have 2 seats empty next to them. So that's the remaining 40 seats. So that's the total 60 chairs on the table. So the smallest number of people at the table would be 60 divided by 3, which is 20. Any questions on this? Okay, let's move on to the third question. Okay, good. 146 is correct. Nidhi, can you explain?
Yeah, so I did this. I just first started with 365 because that's how many days are in the year. Subtracted first in like parentheses, 365 minus 365 over 3 plus 365 over 4 plus 365 over 5. And I subtracted all of that in first to do all 3 of the times that someone's calling. But of course, there's the double, the days that they double called. So we need to add back those days. So I added back 365 over 12 plus 365 over 15 plus 365 over 20. Those are the days that doubled. And then I subtracted again the days that there was 3 calls after that. So that's 365 over 60. That's the LCM also. And after all that, I used a calculator and I got 365 minus 286 plus 73 minus 6, and that's 146.
Okay, good. Yeah, that's exactly right. Do you remember what this kind of technique is called? You're kind of subtracting and then adding actually.
Doesn't it have the word like inclusion or something like that in it? I don't remember the exact name though.
Good. Yeah, that's exactly correct. It's called the principle of inclusion and exclusion. So yeah, let's go over this once more. So this is one way of doing it, of kind of thinking about all the days together. You do have to be a little bit careful in these divisions in that they're not actually, won't be integers. So you have to get the kind of the floor in this of the division, or like kind of make it an integer. But let's actually, I'll go over it in a slightly different way. And yes, this is actually the probably most efficient method of doing this question. But let's, instead of thinking about 365 days together, let's start off with a similar approach, thinking about 60 days. Now, the reason we pick 60 days is that we know, as Nidhi said, the LCM of, we know 1 calls every 3 days, 1 calls every 4 days, and 1 calls every 5 days. So if I think about the pattern repeating, we know the whole pattern will repeat with every kind of the LCM of that. So that would be 3 times 4 times 5, which is 60 days. And let's think about what happens. So the first day, we'll first kind of write out what happens day 1, day 2, day 3, and then think about kind of this inclusion exclusion idea. So day 1, of course, none of the grandchildren call. Day 2, none. Third one, the first one calls. The day 4, the second one calls. Day 5, the third one calls. Day 6, the first one calls again. Day 7, none of them call. Day 8.
The second one comes.
Good, yep. Let's just do 1 or 2 more just to see the overlap. Day 9, what happens?
The
Third.
first called.
First, okay, let's just do a few more. Day 10,
The third one.
3rd. Day 11,
None.
none. Day 12,
The second and the first.
First and second.
good. Yeah, so this is the pattern. So one thing we could do is we could actually go through 60 days and count how many have nones. And if you think about what happens in 60 days, the 61st day, the pattern is going to repeat again. Because I know 3 days was the first, every 3 days was the first one, every 4 days was the second, and every 5 days is the third. So if you have a multiple of 3, 4, and 5, the pattern, all of them will kind of reset. In 3, all reset in 4 and reset in 5. So in 60 days, kind of the whole pattern will reset. So none of them will call on the 61st day, on the 62nd day, and so on. So that's one way of doing it. But now let's just think about within these 60 days, how do we think about how many of these days does the first grandson call? So in 60 days, the first grandson we know calls every 3 days, right? So we know in the 60 days, the first grandson calls the 3rd day, the 6th day, the 9th day, the 12th day. So that's 60 divided by 3 total times, right? So 20 days out of the 60. So out of days 1 to 60, we know that the first one will call 20 times. What about the second grandson? The grandson or daughter. How many times do they call?
He will call 15 times.
Good. That's 60 divided by 4. What about the third one?
12.
12.
Good. 60 divided by 5 is 12. Okay, so one thing we could just do is think about, can we just say that, okay, so the first one calls 20 times, the second calls 15, the third one calls 12 times. So if I think about that, it's just 20 plus 15 plus 12. Will that be the total number of days that the grandkids call, or is that not exactly correct?
There's double counting.
Good. Why is there double counting?
Because of there's the multiples, so like 12, 15, and 20. Those are all repeated in the 3 and the 4, etc.
Good. Yeah, so the example of this is like this day 12 here. So on day 12, both the second grandchild and the first grandchild both called because it's a multiple of 3 and 4. So the problem, if we just think about the days that the first one, second, and third call, we're kind of counting too much because we're counting some days where both of them call together, but we only want to count that as one day because there was a call on that day, and we're trying to figure out the number of days that there were no calls. So if these are the days that one of them called, now let's try to subtract out the days that 2 of them call. And the first and second ones will call together. If the first one calls every 3rd day and the second calls every 4th day, they would overlap on the 12th day, as we saw here. The LCM of 3 and 4 is 12. So how many days are there where the first and second overlap? So if every 12 days they call together, how many days out of the 60 do they call together? Good, 5. So that's 60 divided by 12 is 5. Now, what about the first and third calling together?
Four days,
Good, and why 4?
because it's 60 divided by 15.
Good. And the reason it's 15 is because one calls every 3 days, one calls every 5 days. The least common multiple is 15. So that's 4 days. And what about the second and third?
3.
3. And why is that?
They'll call together every 20 days.
Good. So 60 divided by 20 is 3. So now we've covered the days that first and second call together, first and third call together, second and third call together. So these are the ones we've counted twice. So we can take 20 plus 15 plus 12, subtract out these pairs. Okay, does this give us the right answer? Or are we?
No, because we double counted 60.
Good. Did we double count it, or what is it now? How many times is it counted?
Oh, triple counted it.
Close. Okay, so let's think about it. So if there's a day where all three of them call, is it counted in this number? This is the number of times the first person is called, or the first grandchild is called.
Yes.
Yes. Is it counted here in the second grandchild's kind of number of days calling?
Yes.
And here?
Yes.
Okay, so we first counted it 3 times. Now we started subtracting, right? So we subtracted the times that the first and second called together. Did we subtract it out there?
Yes.
Yes. Okay. And just so we're looking at this day. So let's just say it's some day, but it's day 60, let's say, where first, second, and third are calling together, right? Okay, so we counted it 3 times. Now we subtracted it once here. Now what about here? This is the second and the first and third calling together.
Yes.
Yes, because first and third did call together, so we subtracted it here. And what about here?
Yes.
Yes. So how many times have we counted it now?
6.
We added it 3 times and then we subtracted it 3 times, right?
It would be 0. My bad.
There, good. So now that we counted it, so we're almost there, because if it was just the first and second together, we counted it once with just first, once with just second, and we subtracted out the overlap. So there we're good. If it was just second and third, same thing. We counted it twice because we counted them individually and subtracted the overlap. Now the problem happened because if it really appeared 3 times, we counted them independently, we subtracted out the pairs. Now we haven't counted it at all. So how many times does that happen?
6.
Careful, why 6?
In a 60-day cycle would be just once, but
Good, yeah. Sorry, that maybe, yeah, we're still working on the 60-day cycle. Yeah, so first, second, and third together, we know that happens with the LCM of 3, 4, and 5. So 60 days total. So 60 divided by 60 gives us 1. So in a 60-day cycle, we can add 20 plus 15 plus 12, minus 5, minus 4, minus 3, plus 1. What does this give us?
Mhm. 36.
36.
Let's see. Yeah, good, 36. Okay, so what is this? 36 is the number of days out of 60 days that one of the grandchildren, at least one of the grandchildren called. So what are we looking for?
We want to know how many times they didn't call at all. So
Good.
24 times per cycle.
Yes, so 24 times per 60 days. So what would that be now? So how do we now go from 60 days to 365 days?
That would be 6 60-day cycles, I guess.
Yep.
So that's 144, and then you'd have an extra 5 days. And on the first 2 days in that 5-day section, no one calls. It'd be 144 plus 2, which is 146.
Good, exactly, yep. So if you just think about so doing 60 days, it's easy. We can just multiply by 6. Day 361, day 362, 363, 364, 365 are just 5 extra days. And if you think about what happens, the 361 and 2, there's no calls. 363, the one that calls every 3-day calls. 364 every 4 days, the second one calls. And day 365, the third one calls. So these two have none. So we have to add an extra 2 days, which gives us 146 total. Does this make sense? Okay, any questions?
Yes, it does.
Okay, good. Yeah, so I think as Nidhi kind of mentioned in the beginning, so this approach also completely works, and it's essentially the same thing if you try to work with 365 days together as opposed to 60 days. But the thing you should just be careful of here is thinking about 365 by 3, by 4, and by 5. You have to think about the exact number of days that kind of met this. So that would, in this case, be divided and round to the lower integer, essentially. And this also works completely fine. It's actually maybe even a bit faster than thinking about the 60 days and the kind of gap of 5 days. But I think if you write it out this way, you can kind of see why we have to first count the first days, second, third, and then subtract out the overlaps. And this is this idea of principle of inclusion and exclusion. Now, the kind of extensions of this we can think about is this doesn't apply only when there's 3 kind of sets that we're looking at. If there could be 4, 5, or 6, the same idea where we add the ones individually, subtract out the kind of pairwise ones, add the groups of 3, and so on. So if you're interested, look up a little bit more about this principle of inclusion and exclusion. I think it's interesting, and I think it's not as intuitive when you go for maybe 4 sets or 5 sets, how it kind of extends. But this is the same idea that repeats. So we think about how many fit one of the criteria each, and then subtract out the pairs and so on. Any questions on this? Okay.
Yes.
Yeah, good. Was there a question?
No, I'm sorry.
Okay, no problem. Okay, so that's it for this question. So at the end, we'll just go through, there was kind of an extension problem from last week's on kind of the subset question. Let's see, did anyone have any ideas or answers for this one? Okay, this is a little bit harder, but maybe someone remind me first the approach we took to find to confirm that 76 was the maximum, and what was the idea we did there? And let's start with that to count the number of subsets. Does anyone remember? So how did we find that 76 was the maximum? So we thought about kind of grouping the numbers, right? So we started with 1. So the numbers that 1 kind of could interact with would be 3, 9, 27, and 81. So of these 5 numbers, because they're 3 times each other, we can only pick some of these numbers. We can't put all of them because if we put 1 and 3, they would violate the property, or if we put 3 and 9, or 9 and 27, and so on. So this was one group. Like, what was the next group that we had?
We had another group of 2, 6, 18, 54. Another group of we can't do 3, but we did 4, 12, 36, 5, 15, 45, etc.
Good. Yeah. So let's fill a couple of more to then start thinking about this question. Okay, so 6 is already covered. So 7, 21, 63.
8, 24, 72.
Good.
10, 30, 72. Or sorry, 10, 30, 90.
Good.
11, 33, 99.
Good.
13, 39.
Mm-hmm.
14, 42. 15, 45. 16, 48.
Mm-hmm.
17, 51. 18. Oh, wait. Did we do 18?
Yeah, 18 is covered. Yep.
Oh, so 19, 57,
Mm-hmm.
20, 30. I mean, 2060.
Yep.
2163. Oh, 63 was, oh wait, never. 2266.
Good.
23 of 69.
Mhm.
24. No, 24 was already used.
Good.
25, 75.
Mhm.
20 was 26 used. 26, 78.
Okay.
78. No, 27 was used. 28, 28, 64, 84, I mean.
Mhm.
29, 687.
Good.
39, wait, 30 was used.
Mhm.
So 31, 93,
Mhm.
32, 96, 33, but 34, was that used? 34, 90. Oh, there's not, it'll be over 100, so.
Good. Yeah. So yeah, we can stop there. So that's good. So then after that, it would be 34, 35, 37, and so on. But so basically, how did we get the 76 now based on this? So we looked at each of these groups, right? And we said, okay, for 1, 3, 9, 27, 81, what is the maximum numbers from this set that I could actually take in my subset without violating this property?
Oh,
If I-
so
Yeah, go ahead.
for the first one, it's 3. For the next, for the next one, it's 2.
Mhm.
For the one after that, it's 2, and then all the 3s are 2 as well.
Yep.
Up until 13, that's just 1. All the 2s are just 1 as well. And yeah.
Exactly. Yeah. So we know that we could pick 3 from this. We could pick at most 2 from this, at most 2 from these, at most 1 from these. So if we had, because the problem was if we pick 2 of these, if we pick both 13 and 39 in this set, this would violate because one member 39 would be 3 times 13. Okay, so now that we have this, instead of finding the maximum number, we want to know how many subsets there are with 76 elements. So essentially, the same question is saying, in this subgroup, how many ways are there to pick 3 that satisfy? In this subgroup, how many ways are there to pick 2 that satisfy, and so on? And if I think about each of them as an independent choice, right? For instance, I can pick 13 from this pair and 42 from this pair, and that's a valid set. Or I could have picked 14 from this set, 39 from this set, and that's valid. So basically, I have a choice then for each of these. If I can only pick one of them, it actually doesn't matter which one I pick. And we know there's no kind of interaction. If I pick 20 and 57, that's not a problem. Or if I pick 19 and 60, that's not a problem. Or 19 and 20, and so on. So essentially, the question comes down to how many ways are there to choose the ones from each of these? And I can just multiply that over all the kind of subsets where I have a choice. So let's start off with the first one, 1, 3, 9, 27, 81. I want to choose 3 of them here. What are my choices? Which kind of triples could I have picked here?
1, 9, 81.
Okay, good. Anything else?
That's it.
Good. Yeah, so that one actually doesn't really have a choice. We know we need to take 3 of them, but because we can't really take 2 that are next to each other, we don't have any choices. We have to take 1, 9, 81. We can't take 1, 9, 27 because 9 and 27 would be 3 times each other. We can't take 1, 3, 27 because 1 and 3 would be 3 times each other. So we have no real choices here. Okay, what about this 2, 6, 18, 54?
2 choices,
What are the 2 choices?
2 and 18 or 6 and 54.
2, 18, 6, 54. Anything else?
2 and 54.
Good. Anything else? Why not 1854?
There are multiple, that's a multiple, well, 18 times 3 is equal to 54.
Good. Yes, 18 times 3 is 54. So actually, in this choice, from these 4 numbers, there's 3 possible pairs I could have chosen. So even though the maximum is 2, there's 3 ways I could have chosen these 2. Okay, so now let's move to the next one, 4, 12, 36. How many ways could I choose the 2 from here?
4 and 36.
Okay, anything else?
No more.
Good. So in this case, I need to choose 2 of them here, but since they can't be next to each other, I have to pick 4 and 36. I can't pick 4, 12. I can't pick 12, 36. So there's only one kind of choice I have here. So this doesn't really help me. I know I have to take 4, 36 here. I know I have to take 5, 15 here. And the same thing applies to any of these with 3, right? So 11, 33, 99. What do I have to pick here?
1199.
Good. Okay, so we're kind of done with this point. Let's move to this one, 33, 39. How many choices do I have here?
You have only one, either the 13 or the 39.
Okay, good. Yeah, I have to take one of them. So I have 2 choices, right? I could either take 13 or I could take 39. So two ways here. What about the next one?
There's also 2 ways for the next one.
Good. And the same for, what about this one?
2 ways.
Okay, so and how many times does that repeat?
13.
Close. Let's double check.
15.
So how many rows are there here with 2 numbers?
$14.
Good, 14.
Sorry.
No problem. Yeah, so this is there's a total of 14 of these. I'll write that here. Okay, so now after this point, once we've picked 3296, do we have any more options?
No, they're just one more way.
Yeah, so there's just 34, we have to take 34. There's only 35, we take 35, and so on. Okay, so now based on this, how do we get the answer? What do I do with all these numbers?
You add them.
Careful. So if I add them, I'm saying that I can pick one of these ways or one of these, right? In this case, I could do, for instance, any of these 3 choices, and one of these is a different choice, right? So for instance, I could choose 13 and 218. That's one option, or 13 with 654, 13 with 254. Then it's also 39 with 218, 39 with 654, 39 with 254. So should I be adding or doing something else here?
Multiplying.
Good. So it's multiplying because I can choose one of these and choose one of these, and any combination of those is a valid choice. So for instance, here, if I had 2 choices for this and 2 choices for this, I could say 1314 is one option, 1342 is one option, 3914 is an option, 3942 is an option, and each of these with any of the 3 possible ways here. So I do want to multiply all of these. So what is the product of all of these? You can give it to me as an exponent instead of giving the exact number. What would that be?